Apparent depth and real depth of an object. Apparent depth and real depth of an object existing in denser medium observed from rarer medium observed from a rarer medium observed from a rarer medium. Apparent depth and real depth of an object in a denser medium observed from a rarer medium. Let P be a point object. Let P be an point object existing in denser medium. P is an point object. P is a point object or object point. From the point P, a ray will be traveling. Ray will be traveling along PA. PA is the incident ray and it will be refracted into the rarer medium without any deviation. So this is a ray, and the object point or point object P will appear as P prime. P prime is a virtual image. P prime is a virtual image, and also you can denote a ray that will be traveling along this direction. This is the direction of refracted ray extended in backward direction, and the a ray PQ is incident on the interface separating two media. PQ is an incident ray and QR is the refracted ray which is refracted into the rarer medium. We draw this normal. This will be the normal at the point of incidence Q. This normal is Qn prime, and also we can denote another normal Qn in denser medium. This is a denser medium which has absolute refractive index mu2. Mu2 is the absolute refractive index of denser medium, and also you can denote this is the rarer medium which has the absolute refractive index mu1. Mu1 is the absolute refractive index of rarer medium. Now the point object P existing in denser medium is observed from rarer medium. Human eye is placed in a rarer medium to observe the object point P. This is the object point P which exists in denser medium. A ray will be refracted along QR, and QR ray is extended in backward direction, and it will appear from the point P prime. That's why P prime is a virtual image of real object point P. P prime is a virtual image of real object point P. We can denote the thickness of medium, or the slab, that is T is the thickness of the denser medium. We can denote the real depth of the point object P. HR is the real depth and HA is the apparent depth of the virtual image P prime from the interface. Let HR be the real depth. HR be the real depth of an object point P existing in denser medium. HR be the real depth of the object point P existing in denser medium of refractive index mu2. Let HR be the real depth of an object point P existing in denser medium of absolute refractive index mu2 observed from a rarer medium of absolute refractive index mu1 observed from a rarer medium of refractive index mu1. HR is the real depth of the point object P existing in denser medium, and the point object P is observed from rarer medium which has refractive index mu1, which has the refractive index mu1, and HA is the apparent depth. HA is the apparent depth. A ray of light from the object point P, from the object point P in denser medium, a ray of light from the object point P in denser medium of refractive index mu2 is incident on the interface xy separating two media on the interface xy separating two media normally along PA. A ray of light from the object point P is incident on the interface xy normally along the direction PA and passes along AY in the rarer medium of absolute refractive index mu1 without any deviation. Now from the point P, a ray PA is traveling and it will be refracted along AY without any deviation in the rarer medium. Another ray PQ from the point object P. From the object point P, incident at an angle of incidence I on the interface at the point Q on the interface xy, comma, this is the angle of incidence I of the incident ray PQ, and we can denote the angle of refraction. R is the angle of refraction. Deviates along QR in the rarer medium. Away from the normal Qn prime or away from the normal Qn. Deviates along QR in rarer medium away from the normal Qn at angle of refraction R. On producing back, the refracted ray QR meets the another incident ray PA at the point P prime. Therefore, P prime is the virtual image of the object point P. When seen through denser medium, P appears at P prime. So, an incident ray PQ is incident at Q at an angle of incidence I, and from the point Q, the ray will be refracted along QR at angle of refraction R. Now on producing back, this refracted ray QR will meet with the incident ray PA at the point P prime. That's why P prime is a virtual image. The point P appears as P prime in the denser medium. Using Snell's law at the point of incidence Q. Using Snell's law at the point Q, we get the relative refractive index. Of the denser medium with respect to the rarer medium. We get the relative refractive index of denser medium mu2 with respect to the rarer medium of absolute refractive index mu1, which is given by relative refractive index of denser medium with respect to rarer medium, which is given by 1 mu2 is equal sine r divided by sine I. R is the angle of refraction in rarer medium. R is the angle of refraction in the rarer medium. Now I is the angle of incidence in the denser medium. I is the angle of incidence in the denser medium. Therefore, 1 mu can be written as 1 mu 2 is the relative refractive index, and that is obtained as sine r divided by sine I. Using Snell's law, at the point Q we get 1 mu 2 as equal sine r divided by sine I, or comma mu is equal to sine r divided by sine I. Mu is equal to sine r divided by sine I, where relative refractive index of denser medium with respect to rarer medium. Relative refractive index of denser medium, relative refractive index of denser medium with respect to rarer medium, where relative refractive index of denser medium with respect to rarer medium under bracket 1 mu 2 is denoted by mu, that is mu 2 by mu 1, and that is denoted by only mu, and here we can assume mu as 1 mu 2. Now angle of refraction R equal to angle RQN prime, angle RQN prime, which is equal to angle P prime QN, as angle RQN prime and angle P prime QN are vertically opposite angles, comma, angle RQN prime will be equal to angle P prime QN. RQN prime will be equal to angle P prime QN. Therefore, R is equal to, R can be written as angle QP prime A. R is equal to angle P prime A, where angle P prime QN and angle QP prime A are alternate angles, and angle P prime QN is equal to angle QP prime A. Angle P prime QN is equal to angle QP prime A. Similarly, angle of incidence I can be written as angle QPA. Angle of incidence I can be written as angle QPA. Angle R, this angle of refraction R is equal to the angle P prime QN, and that will be equal to angle QP prime. Here this angle and this angle will be equal because they are vertically opposite angles, and that angle and this angle R will be equal to R, that because they are alternate angles. Now what should be the expression of mu? Mu can be written as mu is sine R by sine I in this case. Therefore, mu can be written as sine R divided by sine I. Putting the expression of sine R and sine I, we get sine angle Q P prime A divided by sine Q P A is equal to, from the triangle Q P prime A, we can write AQ divided by QP prime whole divided by AQ divided by QP. Therefore, mu can be written as QP divided by QP prime. Mu can be written as QP divided by QP prime, where when the angles I and R, when the angles QP prime A and angle QPA are very small, when these angles are very small, in that case the point Q, the points Q and A will be very close to each other. The points Q and A will be very close to each other. Therefore, QP can be written as approximately written as AP, and QP prime can be written as AP prime, which is HA, and HA is the apparent depth. Therefore, mu is equal to HR divided by HA. Mu can be written as HR divided by HA, because QP is approximately equal to AP, which is equal to HR. That is the real depth. Mu equal to HR by HA, which is the refractive index of denser medium. In this case, this angle and this angles, if these two angles are very small, in that case Q and A are, the 2 points Q and A will be very close to each other. Q and A will be very close to each other. That's why QP can be written as AP, and QP prime will be approximately equal to AP prime. QP prime will be approximately equal to AP prime. Therefore, mu is equal to real depth divided by apparent depth. Mu is equal to real depth under bracket HR divided by apparent depth of the object point. Apparent depth under bracket HA. Mu is equal to HR by HA. That means refractive index of denser medium is the ratio of real depth and apparent depth. Mu is equal to real depth divided by apparent depth, which is the refractive index, of the denser medium, refractive index of the denser medium with respect to the rarer medium. Therefore, HA is equal to HR divided by mu. HA is equal to HR divided by mu. HA is equal to HR by mu, which is the apparent depth of the object point P. HA is equal to HR divided by mu, which is the apparent depth of the object point P in existing in denser medium observed from the rarer medium. Observed from the rarer medium. Therefore, apparent depth is equal to real depth divided by refractive index. Apparent depth is equal to real depth divided by refractive index of denser medium. Refractive index of denser medium. Apparent depth is equal to real depth divided by refractive index of denser medium. This is the interface separating denser medium from a rarer medium. This is the rarer medium. And in this case, a point object P exists in denser medium, and the point object P is observed from rarer medium. P prime is the virtual image of real object point P. P is the object point and P prime is the virtual image of the object point P, and A is a point on the interface. We can denote the apparent depth. HA is the apparent depth, and HR is the real depth of the object point P from the interface observed from the rarer medium. In this case, HA equal HR divided by mu. Apparent depth is equal to real depth divided by refractive index of denser medium. Mu1 is the refractive index of rarer medium, mu2 is the absolute refractive index of denser medium. Here mu is equal to 1 mu2, which is relative refractive index of denser medium with respect to rarer medium, which is equal to mu2 by mu1. Now we can denote what is normal shift of the point object P. Normal shift of the point object P observed from the rarer medium. PP prime is the normal shift which is equal to AP minus AP prime. Real depth minus apparent depth is the normal shift. That is PP prime equal HR minus HA. Putting the expression of HA, that is HR divided by mu. Taking common HR, we get HR into bracket open 1 minus 1 by mu. That is PP prime is equal to HR into 1 minus 1 by mu. That is PP prime is equal to T is the thickness of the denser medium, into 1 minus 1 by mu. PP prime is equal to T into 1 minus 1 by mu. That is the normal shift. of the object point P existing in denser medium observed from the rarer medium. PP prime is equal to T into 1 minus 1 by mu, which is the normal shift of the object point P existing in denser medium, comma, observed from the rarer medium. In the diagram, P is the object point observed from rarer medium, and a normal shift will be PP prime. PP prime is the normal shift. PP prime is the normal shift. In this case, PP prime is equal to T into 1 minus 1 by mu, that is the normal shift. HR is equal to T, which is the real depth, which is equal to density, width of the denser medium, real depth or thickness of the denser medium, thickness of the denser medium.